For decades, manufacturing output was limited by the speed of physical labor. As production targets grew, factories had to move away from manual assembly toward automated systems. Early automation relied on cabinets filled with mechanical logic. These relay-based systems were difficult to modify and prone to physical wear, making any change to the assembly sequence a significant wiring project. The programmable logic controller was developed to digitize these mechanical relays. It provided a single solid-state computer that handled complex sequences through software rather than hardwired circuits. Modern assembly lines now integrate robotic precision with high-speed sensors and machine vision. These environments generate data at a scale that exceeds the original scope of factory automation. Managing this increased complexity requires choosing between two different control architectures to run the production line. The PLC remains the standard for operational technology. It is an enclosed hardware platform built to execute repetitive logic in harsh environments. The industrial PC, or IPC, serves as a high-speed computing node. It runs on standard PC components to bring data processing directly to the manufacturing edge. This decision affects more than just processing speed. It determines which department maintains the system and how the factory manages its long-term cybersecurity risk. The PLC remains the industry workhorse because of how it handles time-sensitive physical tasks. It operates on a fixed scan cycle. The processor reads every input, executes program logic, and updates outputs in a strict linear sequence. This cycle repeats at predictable intervals, often 1 to 8 milliseconds, ensuring the machine's response time never varies. This deterministic behavior is required for safety. If a sensor detects an obstruction, the PLC halts the motion instantly, preventing mechanical damage or injury. The hardware is physically designed for this environment. PLCs are fanless, solid-state devices engineered to run for a decade despite high vibration, extreme heat, and electrical noise. However, this rigid architecture is less efficient for non-linear tasks. A standard PLC struggles with the high-level calculations required for complex data analytics or vision-guided robotics. The system trades high-level flexibility for a guarantee of absolute reliability in physical control. The industrial PC operates on a different principle, utilizing standard operating systems like Windows or Linux. Instead of a fixed loop, the IPC uses an event-driven architecture, responding to data requests as they occur to manage multiple tasks simultaneously. This allows one device to run machine vision, AI, and cloud gateways without requiring separate hardware. Utilizing a standard operating system introduces specific trade-offs. General-purpose software is susceptible to background updates and crashes that can interrupt the control logic. Engineers mitigate this by using soft PLCs. This method partitions the IPC hardware, so the physical machine control runs on a dedicated layer, remaining active even if the main operating system freezes. Physical maintenance is also higher for IPCs. They often require more careful thermal management and frequent software updates to protect against the vulnerabilities inherent in open network connections. The IPC provides the scalability required for data-intensive integration, but it lacks the inherent hardware-level determinism of a standalone PLC. The system choice also determines the type of personnel needed to program and maintain the factory. Traditionally, PLCs required an external device to enter code. This separation kept the controller's memory dedicated entirely to the execution of logic. Modern PLCs still follow this model. A laptop is connected to push the program logic and is then removed, ensuring the controller remains unburdened by development tools during operation. The primary language for PLCs is ladder logic. It is a visual language designed to be readable by plant floor electricians, allowing them to troubleshoot the code during a breakdown. An IPC consolidates the entire environment. The human-machine interface, the operating system, and the programming software all reside on the same hardware. Programming an IPC often requires high-level languages like C++ or Python. This shifts maintenance responsibilities away from mechanical technicians and towards specialized software engineers. Your hardware choice directly dictates your staffing needs. You are either empowering your existing maintenance crew or increasing your reliance on the IT department. Understanding the full cost of these systems requires looking beyond the initial purchase price to the total cost of ownership. A ruggedized PLC generally has a higher initial hardware cost than a standard IPC with similar processing power. As application complexity increases, the financial advantage shifts. Scaling a PLC for data-heavy tasks requires additional physical modules, causing costs to rise sharply. An IPC handles these workloads through software, so hardware costs remain stable, making it far more efficient for data-intensive manufacturing. While the hardware is less expensive at scale, IPCs require recurring budget for software licensing and cybersecurity maintenance that PLCs avoid. PLCs are the most cost-effective solution for simple, repetitive control, while IPCs provide better value for operations that rely on heavy data processing. The final decision depends on the specific operational goals of your production line. You should use a PLC for fixed, repetitive automation tasks, where high uptime and simple maintenance are the absolute priorities. This provides a reliable, long-term solution that existing operational technology teams can manage without IT intervention. Migrate to an IPC if your application requires multi-domain control, such as integrating vision systems or direct cloud connectivity. Be prepared to provide the continuous IT support required to manage the security and software updates for an open PC platform. There is no single winner. The choice depends on whether you need the proven reliability of mechanical repetition or the flexibility of a data-driven network.
Thanks for watching. Please visit the channel for more content. Don't forget to subscribe, like if helpful, and comment if something is wrong.